Hello everyone. Today let's discuss about a few questions related to our combination of resistances. Thereby we shall be moving forward to heating effects of electric current, and we shall also be trying to discuss about electrical power. So our topics for today would be question related to combination of resistances, then heating effects of current. Let's start with the first topic. Let's suppose we are given a question that they have given us three resistances. 1, 2, 3. Such that first resistance is of 2 ohm, second one is of 4 ohm, and third one is of 6 ohm. Now they are asking us to combine these resistances in such a way that first we get a R equivalent of 12 ohm, second we get an R equivalent of 1.09 ohm, third we get an R equivalent of, let's suppose, 3.3 ohms. Okay. What do we need to focus over here is that our conclusion. Remember, in series combination, R equivalent is greater than the individual maximum resistance. In parallel combination, R equivalent is less than the least individual resistance. So, in first and second question, we shall be using our result. In fact, we shall be using the same result in our third question, but first let's proceed with the first one. 12 ohm. This is greater than 6 ohm maximum resistance. That means it is for sure that these three resistances are in series. Let's see if we are putting these three resistances in series. This is 2, this is 4, this is 6. What do we have? For series combination, R equivalent is equal to R1 plus R2 plus R3. Solving this, we have 12 ohm. That means to get an equivalent resistance of 12 ohm, we need to group these three resistances in series. Let's come to this one. 1.09. Is this value lesser than the least resistance? 2? Yes. If this is so, then it is for sure that these three resistances are in parallel. Let us draw the combination. For parallel combination, we know our formula. R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. If we just solve this, take LCM as 12, we will have 6 plus 3 plus 2, which is equal to 11 by 12. So our R equivalent becomes 12 by 11, which is equal to 1.09 ohms. Exactly. Now come to this question. 7.33. This is again greater than the maximum resistance. That means it is for sure that 6 ohm resistance will be in series. But what about these two? It is so obvious, if all these three had been in series, then our result would have been 12 ohm. But here our resultant is 7.33. If I am keeping my 6 ohm in series, that means our total resistance 7.33, if you just subtract 6 from this, we'll get 1.33 because 6 is in series. Now, the remaining resistance 1.33, we need to take these two resistance now. 1.33 is less than 2 ohm. That means it is for sure that 2 and 4 ohm are in parallel. And then the resultant combination of these two parallel will be less than the least value 2, that is 1.33. Let's see how a resistance combination would look like. This is 2, this is 4, this is 6. If we just take the combination of these two, what we will have? Equals to 1 by 2 plus 1 by 4. 3 by 4. That means R1 equals to 4 by 3 or 1.33 ohm. We got this result. Then we are taking 6 ohm in series combination with these two. So this combination becomes like this. Now its equivalent resistance would be 1.33 plus 6, that is 7.33 ohms. Getting the point? Okay. Let us switch on to our next topic. Electric current shows at three effects. Chemical effect of electric current that we already studied in 8th standard. Then heating effects of electric current that we shall be studying in this chapter. And then there is one more effect known as magnetic effects of electric current that we shall be taking in our next chapter, which goes by the same name, magnetic effects of electric current. Okay. Let's come to our second topic. Heating effects of electric current. What is happening inside a conductor that current is showing us a heating effect? Okay, let us take it like an example. Suppose this is our conductor. Okay, in neutral state, what happens? Let us draw this conductor over here. The electrons on the upper surface of the conductor, they move in random direction. Anywhere, such that the average speed of these electrons is very less or nearly equal to 0. Now, what happens when we give this end and this end a constant potential, such that after some time we will get a constant potential difference. Alright. Now I am joining these two ends, let's suppose by a battery, such that this end becomes positive terminal and this end becomes negative terminal. So what happens with our electron? The potential difference across the ends of this conductor try to give these electrons a sudden push. When these electrons get a push forward, they accelerate in a set direction. The important thing to notice over here is a set direction. All these electrons would experience a force, a drifting force, and they would try to move in this direction. When charges are moving in a set direction, we say that our current is flowing through our conductor. So, if the direction of electron is towards the left, then our direction of current would be like this, that is towards right. This is our current. Now, what is happening over here? Just assume this conductor as the upper surface. So, this surface just beneath this upper surface will be having the nucleus of the atom and other electrons, right? When these electrons move in a set direction, what happens? These electrons tend to collide with the other electrons or the atoms of the surface beneath. When these electrons collide with those atoms or electrons, what they do? They tend to transfer their energy to those electrons and atoms on which they are colliding, right? When they are transferring their energy to those atoms or electrons, but those nucleus of the atoms and electrons, they are not free to move in a set direction. But what they can do? the atoms which are present over here, or electrons that are present over here, whenever these electrons collide with them, they give their energy to this atom, right? When they are giving their energy to this atom, these atoms start to vibrate at their own position. Now, when they are vibrating at their own position, that means they have gained some kinetic energy. And we have already studied that kinetic energy inside any body or for any atom is always associated with its temperature. Once the kinetic energy of these colliding atoms or electrons get increased, the temperature of the whole conductor starts increasing, and we say that our electric current has shown a heating effect. Now, if I am saying that electric current is showing our heating effect, that means there must be some practical applications based on this. Of course, there are. Have you ever touched a bulb which has been blown for straight 2 hours? The upper surface of the bulb gets hot. Why? Due to heating effect of electric current. Also, due to the heating effect of electric current, what happens? You must have used your heating rod to heat up the water in a bucket, right? Those heating electric rods are using the heating effect of electric current. When current passes through that conducting coil is somewhat like this. When current passes through this coil, suppose these are going to a battery or source. When current passes through this coil, what is happening? The upper surface of this whole conductor, the electrons on the upper surface, इसको काट देना सर. Other application of our heating effect of electric current are the heating electric rods used in our homes for heating up the water, right? Now, what happens over here? Suppose this is our heating rod. Okay, this rod, the upper ends of the rod are going through any source, AC source or DC source, such that the upper surface of this conductor, the electrons on this surface, they collide with the electrons and atoms beneath. Ultimately, what they are doing, they are increasing the kinetic energy of those atoms and electrons, and hence the temperature of this whole coil increases. When the temperature of this whole coil increases, if we just insert this coil inside any bucket full of water, this coil gives out its heat to the water, and ultimately due to the transfer of that heat, our water heats up. Its temperature increases. Another application of heating effect of electric current are our electric press used to iron our clothes. There also it is having a simple coil which heats up due to the current, and ultimately we get our wrinkled clothes ironed, right? Okay. Let's move on to the fact this heating effect of electric current was first noted by Joule, and Joule observed that the heating energy so produced due to the current, that heating energy was directly proportional to the amount of current flowing through our conductor. This heating energy was also proportional to the resistance of our coil. The higher the resistance, the higher our heat energy is. Also, he has noted that this heat energy is directly proportional to the amount of time for which the current has been flowing through our resistor. This effect, let's suppose we are having our resistance and time constant for any coil. Okay, so what happens when more amount of current flows? You must have observed that a bulb which has got same resistance and for the same amount of time, if through that bulb less current is being flown, then bulb glows less, right? Because heat and light are interrelated. If heat is more, light would be more. If heat is less, light would be less. So when current increases, our bulb glows brighter. When current decreases, our bulb gets dimmer. This is called heating effect of current or heating law of current. Now, over here, if we are making our current through any conductor constant and our time also constant, then for a conductor whose resistance is more, heating effect would be more, and for a conductor whose resistance would be less, heating effect would automatically be less. Take it as electric iron. A light iron gives you a less heating effect, while a heavy iron, which is being used by a laundryman, gives you a more heating effect, right? So this one is known as heating effect So this one is known as heating law of resistance. Coming to our third one, time. Keeping our current constant, our resistance constant. If the current through any resistor is being flown for more amount of time, we will get more heat. If the current through that resistor is flown for less amount of time, we will get less heat. How? Take the same example of a heating rod. If water is to be heated up using a heating rod, for lesser time, less amount of water gets heated up, right? But for more amount of time, if you just leave this current through that heating rod for a longer time, what would happen? Our water gets heated up more, right? So this law is known as heating law of time. Combining these three, we have H is proportional to I square R T. Okay, here it has been observed that as current being increased in all the experiments, the heat that so produced was proportional to the square of our current. Okay, that's why our Joule's law of heating, this equation, has I square. If you are giving 2 ampere current, heat would be 4 times. If you are giving 3 ampere current, heat would be 9 times. When we are removing this proportionality sign, so through his experiments, Joule's observed that the amount of heat so produced was only depending upon the square of the current and resistance and time. So this could be easily substituted by equality sign, and we have our equation like this. This is known as Joule's heating law because it was given by Joule's. Alright. Let's come to our next point known as electric power. But before switching to electric power, let us discuss a few key points. This is any conductor, right? Doesn't matter if we change the polarity of our potential. Once this is positive, this is negative, current flows in this direction. In the next part, we are keeping it positive and making it negative. So current would be flowing in this direction, but resistance and time are remaining constant, right? So our heating effect or the heat so produced does not depend on the polarity. It only depends upon the amount of current flowing through any conductor. Doesn't bother about whether the current is flowing rightwards or current is flowing leftwards. For both the cases, it will be showing our heating effect. Alright? Next thing, so that means for AC current, alternating current which is switching its direction after every half cycle, or for DC current, that means direct current which is flowing throughout in the same direction, our heating effect will be same. That's why all our appliances, be them our heating coils, be them our heating rods, be them our geyser or electric iron, or likewise any instrument which work upon the heating effects of electric current, all these instruments work fair for AC as well as your DC. Alright? Next key point to be noticed over here is that if no current goes or pass through any conductor, then no amount of heat shall be produced. Right? Because we are studying heating effects of electric current. For that, our main key factor is the electric current. It has to be passed through your conductor so that our effects are being shown. Alright. That be it in heating effects of electric current. Let's move on to electric power. Our next factor is electric power. Now, what do we mean by electric power? Power in normal sense is nothing but, as we are being studying since our previous classes, it is the rate of doing work. Now, our work is easily related with the amount of energy. So work is nothing but, in case of electricity, work is shown in the form of our heat energy. Okay, this heat energy we shall be using the term E for electrical energy, because ultimately our heating energy is in the form of electricity. So we shall be using the term electrical energy instead of heat energy. So power equals to electrical energy per unit time. That means whatever power is, it is the measure of rate of electrical energy. Also, if we need to take the normal definition of power, so we shall be saying that it is the rate at which our source, be it battery or AC source, does work, but in what? In maintaining a continuous potential difference across any conductor. That be the technical definition of our power, and in short note, we say that power is the measure of rate of electrical energy. Alright. Here, from here, what do we have? Power equals to electrical energy upon time, right? This energy is nothing but I square RT on T. T and T gets cancelled out. So, our power equals to I square R. But there is one more equation that we get for power using our Ohm's law relation. V equals to IR. When V equals to IR, then I equals to V by R. Substitute it here. Instead of I, we write V by R into R. So, we get another relation for power as V square by R. So whenever we are given a parallel circuit, in parallel circuit we shall be using this formula to find out our power, but in series circuit, since current is same, so we shall be using this formula to go to our ultimate result. Alright? Okay. Now let's come to a few questions related to it. Let's come to a few questions. First, I shall be taking question related to heating effects of current. Normally, in boards classes, questions related to heating effect of current comes in the form of ratio questions, right? Where we need to compare the values of heat so produced before and after some change. Let's see how. Let's suppose initially we are given a conductor. If we are given a conductor, so let's assume its resistance is R and some I amount of current flows through it. Such that after T time it produces heat equals to I square RT. This is one thing. Now, they are saying that if the resistance of the wire has been changed to 2R, when the resistance of the wire has been changed to 2R and there is nothing given about your source, that means the potential difference V dash will be equal to initial potential difference, right? When R is changed to 2R but new V is your only old potential difference, then your current by the relation V equals to IR. By this relation, your current becomes V dash by R dash, which is nothing but I by 2. So now after T time, the new heat that shall be produced equals to I dash square R dash into T. I dash is what? I by 2 square. R dash is what? 2R and our time is T. So our new heat so produced equals to I square RT by 2. That means our new heat will be half of our original heat produced when the resistance of our conductor is increased to 2R. Alright. Let's come to another set of question where instead of resistance, the current through our conductor has been increased. Let's say initially our heat equals to this only. Now, current through the resistance has been increased to 2I, right? But resistance is same. When current is increased but resistance is same, if it is given in the question that keeping the resistance of any conductor constant or current has been increased to twice its value, then what would be the new heat so produced? Let's come to the question. From this relation, V would be changed to, from the equation V equals to IR, V would be changed to I dash into R dash, that means 2V. Okay. Our new heat, either you use this thing, voltage in the form of V, that is V square by RT, or you use this one because resistance is not changing, time is not changing, only one factor is being changed over here. So our new heat would be I dash square R dash into T, which is equal to 4I square RT equal to 4H. So new heat is increased to 4 times the value of your old heat. Now, if in the question it had been given that only the current is being increased to twice its value, keeping the potential or our source constant or for the same source. Then V dash would be equal to V only. From the same relation, our R would become V dash upon I dash, which is equal to V by 2I, that is R by 2. Now coming to our here, our heat is equal to what? I dash square R dash into T. I dash square would be 4I square. R dash is R by 2 into T. So ultimately we get this one. So now our new heat, when our source is being kept constant and current has been increased to twice its value, our new heat becomes 2H. Only these kind of questions are being focused in your board exams that you need to bother about. Alright, let's come to a question related to electric power. For electric power, have you ever noticed when you have gone with your parents to buy any bulb or tube light or any electrical appliance, there is some values specified on your electric appliances. For example, for a bulb that you must have bought along with your parents, on that bulb you must have seen that such kind of specifications are given. 100 watt, 220 volts. That means whenever the bulb is being supplied a potential difference of 220 volts, it would give you a power of 100 watts, right? These values specified on your electrical appliances is known as rating of appliance. Based on this rating, now what is the use of this rating? This rating helps us to find out the actual resistance of our electrical appliance. How so? We shall be taking this concept over here. But remember, this rating of appliance is also known as power rating or voltage rating. Alright, let's see how we are going to find out the resistance using these two specified ratings. Since these are our specified ratings, so we shall be denoting it as PS and VS. PS is given out to be 100 watts. VS is coming out to be 220 volts. Let's suppose this same bulb is being used across a 220 volt source, then it is giving you 100 watt power. This specified rating means this. Okay, now 100 watt power equals to I square R or V square by R. In this case, we are relating power with our voltage. So resistance would be V square by P. And in this case, this resistance comes out through our specified rating. Hence, Vs square upon Ps would be our resistance. Let's see what our resistance we get in this case. 220 into 220 upon 100. 484 volts. Okay, now how we are going to use this resistance in our questions? Like this, because in our questions, it won't be giving us only 220 volts. In our questions, they shall be giving us either 200 volts or 250 volts. Let's first take a case of 200 volts. when in the question applied voltage is less than our specified voltage. So now for the question, for solving of the question, of course, when our potential difference is being changed, nothing changes in our resistance value. This keeps constant, this is changing. That means our applied power will also be changing. So now we shall be using our new power with the help of this resistance that we have taken from our specified readings. How we are going to get our power? In this case, our applied power would be VA square by R. VA square is 200 into 200 upon 484, right? Solving this, we get somewhere around our value 82.6 watt. So here when applied voltage is less than our supplied voltage, in that case our applied power will be less than the rated power, right? Here this power is coming out to be 82.6, which is of course less than our 100 watts. So our bulb will carry on to be glowing, but now with less power. Alright, if bulb is carrying on glowing with less power, that means bulb will be dimmer in this case. So here appliance works. If it is a bulb, then it gets dimmer. Okay. Let's move on to our next case, where let's suppose our applied voltage is 250 volts. When the applied voltage is 250 volts, in that case our applied power would be 250 into 250 upon 484, which comes out around 129.2 ohms, which is greater than 100 watts. When our applied voltage is greater than the supplied one, then our applied power comes out to be greater than the supplied one. In that case, our heating effect of current is more than what it could take, right? Heating effect is when it is more than what it could take, then it would simply get the wire or the conductor melted down. So in this case, our appliance damages, or what we could say that our bulb damages or gets fused. Alright. And in the case when our applied voltage is almost equal to our rated voltage, then our bulb or appliance goes at its maximum efficiency or maximum power. So when VA equals to VS, that means PA equals to PS. So here our appliance works at its maximum power. That with the use of our electric power rating. Okay, let's solve one more question related to it, and then we shall be concluding our chapter. Questions come somewhat like comparison of bulbs. Let's suppose we are given two bulbs in series combination such that their rating is 50 watt over 100 volt, again 50 watt, or let's take it as 60 watt over 100 watt. Alright. Next, 25 watt over 100 volt. Alright, let's see if these two bulbs are kept over a potential difference of 100 watt in a series combination. For the first bulb, let's suppose this is B1, this is B2. For the first bulb, our resistance would be what? V square by P, 100 into 100 by 50, which comes out to be 200 ohms. For our second bulb, our resistance would be what? Again V square by P, 400 ohms. Alright. Now, we can simply, let it be like this. B1 equals to 200 ohm, B2 equals to 400 ohm. If it is applied over a potential difference of 100 volts, let us take out, since it is a series combination, so we know one thing for sure, that current flowing through this circuit would be the same, right? When current flowing through this circuit is same, so let's take out our current. Current equals to potential difference divided by R equivalent. For series combination, R equivalent would be R1 plus R2, 200 plus 400. That is, our current is 1 by 6 amperes. Alright. Now, this current goes through bulb 1 and bulb 2. So, for bulb 1, let's see, using this current and this resistance value, what is our power? So, P1 would be nothing, I square R. If P1 is I square R, then let's just solve it. 1 by 6 into 1 by 6 into 200. Solving this, we have 200. Okay. 50 divided by 9, which is almost equal to 5.55 watt. P2 again equal to I square R2, which again comes out to be 1 by 6 into 1 by 6 into 400, which would be equal to 100 by 9. This comes out to be 9.99 watt. Okay, look over here. P1 is 5.55 watt. P2 is 9.99 watt. This value is lesser than our supplied one. This is also lesser than our supplied one. When the values are lesser than our supplied ones, then our bulbs will keep on working, but they will glow dimmer. Just that. Okay. Let us see some other case where what happens if we increase our potential difference. Will our bulbs damage or not? Let's suppose now we are giving them some potential difference of let's say 400 volts. When we are giving potential difference of 400 volts, so our I would be, okay, let's keep it 300. I would be 300 upon 600, that is equal to 1 by 2 amperes. When I is 1 by 2 amperes, again going through the same approach, P1 would be I square R1, 1 by 2 into 1 by 2 into 200, which would be equal to 50 watts. P2 equals to I square R2, which is again equal to 1 by 2 into 1 by 2 into 400, which be equal to 100 watts. So now in this case, P1 is our 50 watts, while our P2 comes out to be 100 watts. So bulb 1 glows at its maximum power or maximum brightness, while for the bulb 2, as soon as it is set over our battery, bulb 2, power of bulb 2 is greater than its supplied power. That means our bulb 2 damages. When in series combination, one appliance damages, circuit gets opened up. When the circuit gets opened up, that means now no current flows through this circuit. So for a fraction of second, bulb 1 glows at its maximum brightness, but after that, as soon as bulb 2 gets diffused, our bulb 1 also stops working because it was our series combination. Likewise, you shall be getting questions on your parallel combination also. In those questions, just make sure instead of using your current, that means our formula for parallel combination, you should be focusing on must be V square by R. So that be it for today. Thank you. This was your electrical power. Only thing remain is our domestic circuits, but the same topic is already being taken in your magnetic effects of electric current. So we shall be taking that topic in our next chapter, magnetic effects of electric current. Thank you.